Far beyond the warmth of the sun, where sunlight grows faint and the cosmic cold takes hold, lies a world wrapped in enigmatic quiet, Uranus. It is a planet unlike any other, spinning sideways as it drifts through the outer solar system. Its pale, icy blue atmosphere shrouds secrets as old as the solar system itself. For decades, Uranus appeared tranquil and unchanging, a serene orb of cool gases with no sign of the violent storms that rage on its giant siblings. Yet, just as explorers unearth hidden caves in the darkest forests, astronomers have discovered a shadow lurking within Uranus' atmosphere, a vast, swirling mystery known simply as the Great Dark Spot. This ominous, shifting patch defies our early expectations of Uranus as a calm world, revealing instead a dynamic and turbulent realm. It is a storm of such scale and complexity that it challenges our understanding of planetary atmospheres, hinting at forces both strange and powerful. The Great Dark Spot is not merely a weather pattern. It is a symbol of Uranus' hidden nature, a ghostly fingerprint etched across a distant blue canvas. The unveiling of Uranus' Great Dark Spot came as a shock to the scientific community in 1986, thanks to the unprecedented visit of NASA's Voyager 2 spacecraft. As Voyager 2 approached the icy giant on its historic grand tour, its instruments revealed a world that was far more complex than previous telescopic observations had suggested. Among Voyager's most startling discoveries was an immense, dark oval-shaped storm situated near Uranus' equator. This feature spanned thousands of kilometers, roughly the size of Earth itself, appearing as a stark shadow against the planet's otherwise pale and uniform atmosphere. This discovery upended the long-held notion that Uranus was a quiet and inactive planet. Scientists quickly began comparing the Great Dark Spot to Jupiter's famous Great Red Spot, but found the two were fundamentally different. While Jupiter's storm is a high-pressure anticyclone persisting for centuries, Uranus' spot seemed to be a transient, ever-changing phenomenon. This raised profound questions. What powers such a storm in the cold outer solar system? How does it evolve? And what can it tell us about the planet beneath? Peering into the Great Dark Spot means delving into the intricate layers of Uranus' atmosphere, a mixture dominated by hydrogen, helium, and methane gases. Methane absorbs red light, giving the planet its characteristic blue-green hue. Yet the spot itself appears much darker because it disrupts these layers, allowing less sunlight to reflect back into space. Scientists believe the Great Dark Spot is a massive vortex, a swirling storm of gas and clouds extending deep into the atmosphere. Winds within this storm race at incredible speeds, reaching over 900 kilometers per hour, fast enough to rival the most powerful hurricanes on Earth, yet on a scale thousands of kilometers across. Above the dark core of the storm, bright white methane ice clouds form small, bright companions that orbit the vortex like satellites. This vertical structure hints at complex atmospheric dynamics, where methane clouds condense and evaporate, feeding the storm's energy. Beneath the visible clouds, heat escaping from Uranus' interior, combined with subtle influences from solar radiation and Uranus' extreme axial tilt, likely stirs atmospheric currents. These forces combine in a delicate balance to create and sustain such a massive, dark vortex, one of the most fascinating weather phenomena in our solar system. Perhaps nothing defines Uranus more than its extraordinary tilt. Unlike any other planet, Uranus spins nearly on its side, tilted about 98 degrees relative to its orbit. Imagine a spinning top that wobbles almost flat, This unusual orientation results in extreme seasonal shifts lasting over 2 decades. During its long seasons, one pole faces the sun continuously for about 42 years, while the other plunges into decades of darkness. This produces atmospheric conditions unlike anywhere else in the solar system. The Great Dark Spot may be born of these seasonal extremes. The long periods of sunlight and darkness create temperature gradients that drive complex winds and storms in the atmosphere. This, combined with internal heat escaping slowly through the thick clouds, could be responsible for generating vortices like the Great Dark Spot. Understanding how Uranus tilt shapes its weather is key to unlocking why these dark storms appear, evolve, and disappear, making Uranus a natural laboratory for studying atmospheric physics under conditions vastly different from Earth or even Jupiter and Saturn. The story of Uranus' Great Dark Spot grows more mysterious with time. When the Hubble Space Telescope turned its powerful eyes toward Uranus in the years following Voyager 2's flyby, the original Great Dark Spot was nowhere to be seen. Its disappearance puzzled astronomers. Had the storm simply dissipated? Had it moved to a different latitude or faded beneath higher clouds? Or was it obscured by changes in atmospheric conditions? Hubble later discovered new dark spots emerging in different regions of Uranus' atmosphere, suggesting that these dark vortices are not permanent but transient features, appearing and fading over years or decades. This ephemeral nature contrasts sharply with Jupiter's Great Red Spot, which has persisted for centuries and suggests fundamental differences in atmospheric chemistry, energy sources, and dynamics between the ice giants and gas giants. The shifting presence of these dark spots is a vivid reminder of how much we still have to learn about planetary weather systems far from the sun's warmth. Uranus shares many characteristics with its neighboring ice giant, Neptune, similar in size, composition, and distance from the sun. Yet their atmospheres behave in markedly different ways. Neptune's own Great Dark Spot, discovered by Voyager 2 in 1989, also appeared and then disappeared within a decade. Its storms tend to be more active and frequent, reflecting Neptune's higher internal heat output. Scientists study these dark spots on both planets to understand why similar worlds can host such different weather. What roles do internal heat, atmospheric composition, and magnetic fields play? How do solar radiation and seasonal cycles interact to drive storms thousands of kilometers wide? Comparative study of these two ice giants sheds light not only on our solar system's outer planets, but on the nature of numerous exoplanets discovered orbiting distant stars, many of which resemble Uranus and Neptune in size and temperature. The Great Dark Spot on Uranus is more than an atmospheric curiosity. It is a key to understanding the planet's internal processes, how heat flows from its core through layers of gas, and how energy drives weather on a world vastly different from Earth. Studying this storm teaches us about fluid dynamics under extreme conditions, where temperature, pressure, and composition combine in alien ways. Moreover, the knowledge gained helps prepare for future missions. Uranus has never been explored in depth since Voyager 2's fleeting encounter. Understanding phenomena like the Great Dark Spot is essential for designing spacecraft that could one day orbit Uranus, mapping its weather, magnetic environment, and even searching for signs of habitability on its moons. Finally, the Great Dark Spot informs our broader search for life and planetary formation across the galaxy. By studying ice giants close to home, we refine models to understand the diversity of planets orbiting other stars and the dynamic forces shaping their atmospheres. As Uranus spins slowly in the twilight of the solar system, the great dark spot drifts, a silent sentinel of change and mystery. This transient shadow, shifting and evolving, is a beacon for future explorers, an invitation to uncover the secrets locked beneath the icy clouds.